Hi guys, how's it going? I hope you're doing well and you're safe and relatively happy in these times. We're on to lesson 3 of this unit. As always, please don't forget to upload your homework when you're done to Edsby. And if you have any questions, a lot of people have been now meeting with me by video, which is great, and it's a lot easier to connect. But you can also just type in your questions if you want, and I can answer them that way or provide a solution. Okay, the first one here, you can try these warm-up questions if you'd like by yourself and then check your answers, see how you're doing. Otherwise, if you're stumped, you can always watch this video. Okay, I'm going to begin. So first one here, we're looking for exact values for x between 0 and 360. First one, I got sine x plus root 2 equals negative sine x. So I need to move all of my sine x's to one side. So I'm going to add sine x from the right side into the left side. So that's going to give me 2 sine x's on the left side. And at the same time, I'm going to move this root 2 over here. So that becomes minus root 2. And then I need to divide both sides by 2 because I've got 2 sine x's. So I have negative root 2 over 2. Great. So we now have it set up so we can isolate for x. So remember, if you think of your exact values, this alpha here is going to be, or our related acute angle is going to be 45 degrees because that comes from this guy, the root 2 over 2. The other thing we have to consider is that this negative for sine means it's going to be in which quadrants. So you can think of it as the number system, so quadrant 3 and quadrant 4. Or if you would prefer, you can always just sketch it, knowing the cast rule. So I know that because of the cast rule, it's going to be down here in these two guys right here because sine is negative. So I can go ahead and draw my two triangles that it's going to form. My related acute angle is inside, and then what I need to figure out is alpha 1, or theta 1 rather, and theta 2. So I got theta 1 is 180 plus 45 degrees. So that's going to be 225. And then the second one here, theta 2, is going to be 360 minus 45. So that's 315. So it is called x in this case, so therefore it's not theta, it's x equals 225 and 315. And we're good. So hopefully that's not too bad. Next one's a bit trickier, but not too bad. So we got 3 tan squared x minus 1. So remember, this is not x squared, it's the tan is the squared part, so the whole thing squared. So if I start to solve and isolate for tan x, I have 3 tan squared x. I'll move the 1 over, so that becomes positive 1. I can divide both sides by 3, so that becomes 1 over 3. And now because I've got the squared, I get to take the square root. Oops. Get rid of the squared. And so I end up with the square root, and I have to take the plus or minus of this. So I have plus or minus the root of 1 over 3, which I can simplify because the square root of 1 is just 1. So I have plus or minus 1 over root 3. So tan x equals this. So because I have plus or minus, what that indicates is that really what I have is all 4 quadrants that's possible for tan. So I've got really the whole bow tie I could draw if I wanted, like this. It's really any one of those 4 possible angles. What I do need though is alpha. So alpha in this case, 1 over root 3. I always try to remember, because it's 1 and tan is opposite over adjacent, the opposite to 1 is the smallest angle, which is 30. So I know that all of those alphas are 30. So you can go ahead and figure out each one. So therefore, x equals 30, obviously. The next one's going to be 180 minus 30, which is 150. The next one in quadrant 3 will be 180 plus 30, so 210. And then the last one's 360 minus 30, which is 330. And we're good. So you can figure those out in separate calculation if you want. Okay, today's lesson is kind of a departure from basically everything we've been doing with trig functions, but it's related in that it uses all of those things. And it's called trig identities. And it's really the first time that you look at proofs in math in high school. And so you use concepts about trigonometric functions and relationships between them in order to prove different equations. And so in this, we have basically a toolbox of what are called identities. And the toolbox is the thing that you go to help prove things. So these are the things that are always going to be the case. So there are some ones we did in our first lesson, which is the primary trig identities. And this is like sine is 1 over cosecant, or cosine is 1 over secant, and tan is 1 over cotangent. And so that also can be flipped with the reciprocal, and so you can have cosecant's 1 over sine, and so on. So all of those should be new in terms of what we're going to use them for. And then the quotient one, we saw this briefly, but tan is the same as sine over cos. And so we proved that when we had sine is equal to y and cosine is equal to x, because tan is y over x, then it's just tan equals sine over cos, or y over x. And then you could take the reciprocal of that, so cotangent is actually cos over sine. So you just flip that ratio there. The other one, which is called the Pythagorean identity, which is this thing here, is going to be something we're going to use quite a bit. And there's a proof, and I provided it here. And so you can actually, this is another little GIF thing I created. Anyway, so you've got this x squared plus y squared equals r squared. And you can follow along here. Basically, we get to this point here where x over y is really just cos, and then you get the Pythagorean identity. So you don't need to know this thing, but I think it's good to see where it comes from. I'll just let it replay again. And so you get x over r squared, which is the same as cos theta squared, and y over r squared is the same as sine squared. So this Pythagorean identity is something we're going to use, and it also has another couple forms. So you can rearrange this so you could have sine squared equals, and you move the cos squared x over, so you have 1 minus cos squared x. And then you can have cos squared x, where you move the sine squared x over, so 1 minus sine squared x. And it's a bit confusing in the beginning in what we're going to be doing with these things, but it all makes sense once we start to do some questions. So there are some general rules you need to follow. Generally, and it's not 100%, there are always exceptions, but generally what we're going to do is you use these identities or these tools to write equations in terms of sine and cosine. So what that means is, so for example, instead of having a reciprocal, let's say I had cosecant, I would replace cosecant with 1 over sine. So i.e. replace reciprocals. Another example would be, let's say I had tangent. So tan of theta is sine over cos. I would replace tangent with sine over cos. So generally you try to work with just sine or cosine. Another thing to watch out for is if you see anything squared, like sine or cosine squared, it's often you're going to use the Pythagorean identity, which is this thing here. And again, this will make more sense as we go through. And then there's some general algebra stuff that you can try, and this will make more sense once we actually try to do this. So just so you're aware, you will be given almost all of these identities. You'll have these given on a test, and you'll have this given on a test as well. And so if you were to look up all of the possible identities, this is just the beginning of trig identities. I could fill 2 pages, and I remember in university getting front and back page of just these tools that you have to use in order to figure things out. So it does get a lot more complex. So the good thing is we're going to start relatively slow. So when we're looking at these things, what we're trying to do is I want to show that this equals this, for example. And as you see it, obviously it doesn't look like they're the same, but what we have to do is to use those tools, the identities, to figure this out. One of the things you do is you are not allowed to move things across the equal sign. You have to do everything on the left side or everything on the right side. So I can't divide things across the equal sign. So just to make this clear, this is equal to here. That's not easy to see. So when I start these questions, you basically, you pick a side. You say, okay, which side has more things that I can work with? And knowing the general rules that I mentioned, like you always try to replace tangent, or you always try to look for things that are squared, or if there's reciprocals, you replace them so you can get sine and cosine. So that gives you a good idea of what to use. So I just basically say, okay, I'm going to start here with the left side because there's more stuff on it and I see there's a tangent. So I'm going to rewrite the first line and I say left side equals. And then I do the same thing just so I have it on the right side. Oops. Right side equals sine theta. So that's step one. The second step here, and it's always going to be different depending on what you have in your equation, is to look for things that you can replace. So I'm going to here replace tan. So I'm going to take away tan, and I'm going to write what tan is equal to. And tan is equal to sine theta over cosine theta, like that. And so now I have something that's different that generally is going to allow me to simplify. And so this one is a very simple example, but generally after you replace something, you want to simplify if you can. And so in this case, if you look at what we have for simplification, I have really cos theta over 1 times sine over cos. It's really cos divided by cos. So those can go away. And I'm left with just sine theta. And notice we have the same thing as the right side. So therefore, the left side equals the right side. And we've proven the original statement, which is cos times tan equals sine. That's an example of a proof. So you do not move things across left to right or right to left. You just stick with one side and the other side. Let's try some more. Really, the more you're going to do of these, the more it will become just second nature. And sometimes it's like little puzzles, and I think it's good to practice it. So I'm going to start here with left side equals, and notice there's a lot more on the left side, so we might as well start there. So I'm going to rewrite what's given. And then over here, I'll put the right side equals, and that's just 1. Okay, so we look for things that we can replace. See, this one you could probably even try yourself. So I've got tangent. Tangent is the same as sine over cos. So I've got sine x over cos x, and that's all over sine x. So again, after we replace something, generally we can simplify. And so I've got, again, cos can go away. This looks quite similar to the first one. So I end up with sine x over sine x. And it's always good to just glance over to the other side and say, what am I trying to even get this to? And obviously we're looking there and it's just 1. And sine x over sine x is equal to 1. So that equals the right side, and that's our last step. And we say, therefore, left side equals right side. So not so bad. It will get more complex here in a minute. So the next one, we've got left side equals and right side equals. And obviously there's more stuff on the right side, so let's begin with the right side. So I've got secant x minus, tan or sine times tan. So this time we've got a reciprocal identity, so we can replace that. So secant is the same as 1 over cosine. So I'm always trying to get things in terms of sine and cos. So I have 1 over cosine minus sine, and I can also replace the tan. So I get sine x over cos x. And so now I can simplify. There's not a lot we can simplify, but I do have this 1 over cos, so I can leave it. I've got sine x times sine x in the numerator. In the denominators, I got 1 times cos x. So this becomes sine squared x. And remember, we write the squared before the x, like this. So at this stage, notice we've got 2 fractions on the right side. And on the left side, I've got 1 term. So somehow I'm going to have to bring these 2 fractions together and make it 1 term. And generally when you glance over to the other side, it helps to indicate what you should do. Not always, but often it will. And so this time I've got the same denominator, so I don't have to do anything. I can just write 1 minus sine squared x over cos x. And again, we've still got 2 terms on top. So this is where you have to go, and there's nothing obvious to do, but notice, if I highlight here, I've got, what was it, 1 minus sine squared x, which is cos squared x. So I've got this that I can replace. So this is the Pythagorean identity. So this is the Pythagorean identity. I'm just going to write it so you have it in your notes. You wouldn't necessarily write that on an assessment or in your solutions. So that's the same as cos squared x. So now I have cos squared x over cos x. That's the same as like if I had y squared over y. Y squared over y, I would get rid of the squared and that would divide out, and so I just left with something on the top, which is y. So this time the squared gets rid of the whole cos. So I'm just left with cos x, which, as you see, is the left side. So therefore, my left side equals the right side. We're good. Okay, so the next one is an example of how complex it can get. And you're not necessarily always going to get these, but it does get pretty crazy. So I've given you a bunch of space left and right. We're probably going to use all of it. So I've got the left side is this cosecant squared theta minus sine squared theta. And way over here, I'll write right side equals cos squared over sine squared theta. When you do some questions, sometimes it is possible to work with each side separately. So you can actually work on both sides. But generally, you could just do it all with one side. And I think that's how I'm going to approach this because it makes it simpler. So I'm going to pick the left side here. The reason I'm picking that is because I see cosecant squared. Whereas the right side, I don't see anything obvious to replace. So I'm going to pick this left side and I'm going to replace cosecant squared. It's squared, so that means the reciprocal will also be squared. So this means this is the same as 1 over sine squared theta. And then minus sine squared theta. So after you do that, it's really not obvious what to do. The whole idea of, I've got 2 terms on the right and 2 terms on the left, so I've got the number of terms right. This is where you have to experiment, and it's not obvious what to do. What I'm going to do is I'm going to combine these 2 by creating a common denominator. And again, this is kind of a trial and error to see how it goes. And sometimes you're going to end up down a path that's just not going to work and you have to come back and start again. So if I do that, what I need to do is multiply this second fraction by sine squared theta over sine squared theta. So the first one, I still have 1 over sine squared theta minus sine squared times sine squared is really sine to the 4th. And then that's over sine squared. So what I'm doing is creating a common denominator so that I can bring this together. And so I end up with 1 minus sine to the 4th theta over sine squared. The next step is something that's a bit of a trick and completely not obvious, and I wouldn't expect anyone to do this, but what this is 1 minus a perfect square. What I can do is factor this as a difference of squares. So I have 1, which is a perfect square. So I factor as 1 minus, and then sine to the 4th theta is the same as 1 minus sine squared theta, and then 1 plus sine squared theta. And again, at this point, you're probably just following along, and that's okay. These are the kinds of tricks you're going to pick up in order to be able to solve the more complex ones. So now, notice here, I have 1 minus sine squared theta, which is the Pythagorean identity. Pythag. So that's really the same as cos squared theta. And then I get 1 plus sine squared theta over sine squared theta. So always after you replace something, generally you can simplify it. What I'm going to do is I'm going to expand this by putting the cos squared theta in with this. I'm going to have to bring this up over here. So I'll just draw a line so it doesn't look like they're getting together. And so I've got cos squared theta plus, and then I just combine these two. And I'll write the sign first. You don't necessarily have to. Like that. So now I've got everything in terms of sine and cos, and when I look at the right side of the equation, it's starting to look a bit closer at least to what is there. So another thing you can do, notice I now have all of this on the left side as one term. It's really one big fraction, whereas the right side is 2 separate fractions. So what I'm going to do is rewrite this as 2 fractions. So really, because I have 2 terms on top, this is really cos squared theta over sine squared theta. And notice that's the same as the right side of the equation. And then I have a separate fraction now of sine squared theta times cos squared theta over sine squared theta. And so the first fraction I'm going to leave because I know that that's part of the solution for the right side. And then the second fraction, notice I've got now sine squared theta and sine squared theta, and they're gone. And then we end up with the right side. And all of these questions, it will work out that the left side is equal to the right side. So don't be concerned that you're heading down a path that just is going to fool you on an April Fool's Day. So this one is very tricky, but there's some things that I want you to just pay attention to. One being this factoring idea, so the factoring difference of squares. Sometimes that's advantageous. So remember, if you have things that you can factor, it's always possible you can do that. The other is just simply simplifying, like this part here where I put things through, and then always looking to the other side of the equation to try to help you out. So I've split this lesson into 2. So what I'd like you to do is to work on these practice questions. They're not so bad in the textbook. And then next class, what we'll do is we'll go through a bunch together and we'll take them up and I'll give you some more practice stuff. Okay, again, as always,